Hello once again, everyone. Our topic for today is Introduction of Advanced All-in-One Machine for AME and SMT. Before we dive into today's content, I would like to inform you that during the presentation, we put everyone to mute. If you have any questions, please feel free to use the chat function and the reactions. During our Q&A session at the end, if you have any questions, please raise your hand. I will activate your microphone, and then you are able to unmute yourself. If you have any further questions after the webinar, then please visit our James platform and use the contact function. Please be advised that this webinar will be recorded and later we will publish it on our platform. Short note for Windows users: to have a better view of our speakers, we recommend using the option called Gallery at the top. Okay, now let's do the proper introduction. So my name is Alex. I'm the head of marketing and sales at James. In my role, I handle partnership contracts, assist our clients in adopting AME technology, and actively participate in different events and trade shows. Now, I would like to introduce our speaker, Ryojiro Tominaga. He's the section manager for AM development at the FUJI Corporation in Japan. He holds a PhD at the field of organic physical chemistry, and he's responsible for the AME process integration and product design in Fuji's product development in the field of additive manufacturing. Now I will pass the virtual stage to Ryojiro as he delves into the topic of advanced all-in-one machine for AME and SMT. So Ryojiro, over to you. The virtual stage is yours.
Thank you, Alex. And thank you for having us to such a great opportunity. I'm Ryojiro Tominaga from FUJI Corporation. I'm belonging to the Development Center, FUJI in Japan. I'm one of the section manager. So today's my presentation title is the Introduction of the Advanced All-in-One Machine for AME plus SMT. Okay, please me start my presentation. So first of all, let me please briefly explain our company. FUJI Corporation has a 3 divisions. And basically, we are the robot manufacturer. And our biggest and main field is that electrical component mounters and solder printing machines. So we have so many know-how for the SMT and history and result. This is one of the background. We decided to develop the cutting-edge machine for the AME plus SMT. We are calling this machine as a FPM Trinity. So let me double check with you about the definition of the AME first. AME is additively manufactured electronics. So as you well know, additive manufacturing is selective direct deposition. However, current common PCB manufacturing process is a very opposite because of it's applying the most of substrate method. So PCB manufacturing, we etched out the copper on the drilling or laser and the routing. So many subtract process we have for the PCB manufacturing process. But on the other hand, in case AME, additive electronics, we just print that direct material by the inkjet process and cure with the UV exposure. And we also print the conductive material by the inkjet and sinter it with a heater. justice. So process is very simple and very effective for reduce that waste or chemical waste. Therefore, AME is a very beneficial approach to run the product development first, because no initial costs required, and manufacturing can be completed within 1 day. And AME is more efficient, so it can minimize the waste. Factories are very much small, and this technology can be extended to that 3D. So this is the potential of the AME, and maybe everyone is expecting for that AME. So this is the market size. So PCB substrate market going to be $128 billion by the 2030. And market of that additive manufacturing will be grow up to that $76 billion by 2030. And this wrapped area, so pink area, is our target. Here is the market with that additive electronics, and based on that research from the ID Tech, this market will be $2.3 billion by the end of that 2029. But I think that it's a just forecast. So very important for us is we are going to expand this pink area together with that James platform. So as I said, AME is a very beneficial approach. So we are believing AME's effectiveness. We are believer, but then how the SMT needed to be? This is one of the biggest agenda of today, because against the AME, we encounter some inconsistency of SMT. So this is a table to show that common SMT and the common PCBs relationship and the concerns for the AME. For the interconnection, the common SMT applying the solder material, so to make some good bonding and electrical connection. So surface finish for the PCB have to have nickel gold or nickel palladium gold or OSP on the copper to make some good metal alloy like as IMC. And for the solder printing, by the consideration of that high volume manufacturing and low cost, most of that manufacturer are using the screen mass printing. However, in case AME, conducting material is a silver, so we cannot apply gold plating, nickel plating, and the OSP. And AME target is not only the 3D, 2D, but also 3D. But for the 3D surface, screen mass printing is not so adequate. And thermal condition for the reflow process, such a very high temperature process, A common PCB applying the very loyal CTE material and very low dynamic warpage substrate. By that, by using the composite material with the glass. However, in case AME, we have some restriction of the material. So CTEs are very much higher than the common FR4. So it may lead some swelling and warpage. The production line. So one of the important points for that manufacturing process is operation ratio and capacity. Therefore, substrates have to have some compatibility of the material and the condition. However, in case AME, manufacturer concern is material mixing and contamination and condition change. So I think that those are the inconsistency of that common SMT process against the AME. Therefore, we have to consider the drastic changes. So temperature and the material have to be controlled to that low temperature. The screen printing must be changed to the direct deposition process. And line production should be changed to that cell production. So those are today's our proposal. So by those reasons, our machine vision is integration of that every process in one pieces of the machine. So machine name is a FPM Trinity. The reason why we named this machine as a Trinity is the three key important functions. One is resin 3D printing. The second one is circuit formation. The last one is that low temperature SMT. So this machine has those three functions. And data can be imported directly from that circuit card by that Gerber or STL data format. And this machine has a job edit function, panel layout, and we can offer to the customer optimized process parameter. So, so many units and function integrated in one machine. So, function related to that AME is yellow text, and related to that SMT process is a light blue text. So for the AME process, we have two inkjet head and a smart maintenance system for that UV resin ink and silver nanoparticle ink. And as a post-printing process, there are infrared heater and the UV exposure in it. Those are the units used for that AME process. And for the SMT, we have air dispenser and a smart calibration system for the silver paste printing and the epoxy paste printing. I'll explain the detail later. And pass placement we have at the left side. And pass supply unit is a alternative one for that both feeder and the tray. And post pass mounting process. Here is a less heater unit. So those so many units combined and integrated in this machine. So here I'd like to show you the movie to explain the process flow. So right side is a printing area, and the left side is a pick and place and the path supply area. That's first, we print the resin, the build plate by the inkjet system, and for the curing, UV exposure will be done. And after that, we print a silver nanoparticle ink on the surface multiple times, and sinter it by the infrared heater. And we have two dispenser. One is for the silver conductive paste. So we dispense the conductive paste at the terminal of the circuit instead of the solder paste. And after that, we print epoxy glue at the central point of that parts placement. After that, the palette moves to that left side for that pick and placement of that component, and return to that printing area. In the printing area, we have press heater. So by that, with the compression and the heating, parts will be fixed well. And the final process is side filling and curing. So those are the process in our machine. Okay. For the AME substrate, we and our user have to understand well about that strong point and weak point. So weak point of that AME is productivity and quality. So capacity of the traditional PCB factory is very, very bigger than the AME. And density of the circuit and the capability of that SMT process for that high density pitch component. The ME is a little bit weaker. And because of that durability of the material, temperature cycle test, so reliability, of course, the common PCB looks good. So we have to understand that weakness. However, AME has very strong point for the delivery and sustainability design. So AME can manufacture the substrate with a bareboard plus SMT within 1 day and without any initial tooling. And the waste is less than 5% compared to that traditional PCB manufacturing process. And factory size is approximately 1,000. So just one floor, only one floor really. And freedom of the shape and specific gravity of the material is very good. So design capability for that unique shape device or lightweight device, AME has a benefit. So we should understand that weak point and the strong point, and we have to find out that sweet spot application for that AME. Okay, this is the current specification, design rule as of today. So circuit formation, our standard silver thickness is 4 or 7 micrometer, and the minimum range space is 140 to 100. And for the resin formation, maximum resin burst size is 120, and thickness is 4 millimeter. And interlayer connection. So maximum layer count is 5. And the layer to layer interconnection will be formed by the blind by hole. The parts mounting minimum electrode pitch is 0.5 millimeter, and the minimum patch part component size is 0.6, 0.3 millimeters. So as I mentioned, our machine can manufacture the circuit board with mounted component within 1 day. So from the core process and the circuit build-up process to that part mounting process, those processes can be completed within 1 day. So this is just an example. We are repeating that verification of that standard sample manufacturing day by day. So those samples can be manufactured within 1 day. So maybe you can imagine a very fast development, the manufacturing. And direct data import is very important. You know that you achieve that no initial lead time and the initial tooling for the glass mask and the metal mask. So our machine can directly receive that STL and the GABA data from the circuit card. So resin structure data can be exported from the circuit card and changed into that printing design and job, and printed by the inkjet head. And circuit design also exported by the STL or GABA data and converted into the printing design and job for the inkjet process. And for the parts mounting, we also catch the data, the GABA and the BOM, and exchange it to the parts mounting job. And air dispenser automatically dispense that paste to that adequate location. So please let me emphasize again. So AME is a very effective approach for that environmental friendly manufacturing process. So because of direct deposition process and no wet process, no etching process, no drilling, and the laser ablation process or routing process, so we can reduce the waste more than 95%. Okay, please let me explain the more detail about the SMT process. So as I said, for that affinity, that AME process, we have to very concerned about that change the temperature and the printing process and production process. So for by those considerations, SMT process of the FM20 applies silver paste, which can be cured in the low temperature condition. And instead of the screen mask printing process, we use direct dispensing system. And temperature is at just 80 degrees C, very low temperature. And cell production. This is the changing we have. Why we need to minimize the temperature? This is a graph to show the relationship between the peak temperature of the SMT and the substrate swelling, the XY axis. So in case common PCB, CTE and the TG is a very good. So substrate swelling is a very small. But in case common 3D printer, it's just a acrylic material, and it has so high CTE and low TG. So substrate swells a lot. So for the FPM Trinity, we developed a very good material with a chemical supplier, which has very low CTE and a very high TG. But even so, it's not equivalent to the common PCB. Therefore, in order to achieve the same substrate swelling ratio, we have to decrease the peak temperature as long as possible. And by the estimation, we concluded temperature up to be 80 degrees C. But in the 80 degrees C condition, solder doesn't melt. Therefore, we change the material to the silver paste, which can be cured by low temperature condition. The silver paste interconnection is very difficult because there is no self-alignment function, and it is very difficult to control the gap between the printed paste to paste after the bonding pressure. Therefore, we established a very specific and unique low temperature parts mounting process. So at first, we print a silver paste by the air dispenser, and before the parts mounting, we cure beforehand. And this silver paste has a low modulus properties. And after the curing with a low modulus silver paste, we put the underfill material at the central position of the parts mount area. And after the pick and placement of that component, we cure with the pressure. So like as a thermal compression bonding process. And after that, we do that side filling process using the same material as the underfill. So every curing process, silver paste curing, parts mounting, and the thermal compression process, and the side filling and the curing process, every process is less than 80 degrees C. So the reason why we adapt the silver paste, which has low modulus properties, is to minimize the stress. So this is a CAE result. And this data is showing that stress, which concentrated at the edge of the component. So interface with the electrode and the silver paste. So if we apply the common silver paste, a very rigid one, stress concentrate to the interface. But in case we reduce the modulus of the silver paste, stress can be minimized. So this is the result. So by applying the low modulus silver paste, we can reduce that stress 75%. So in order to avoid some crack defect, which is led by that concentrated stress, we decided that we concluded we have to apply the low modulus silver paste. And also, silver paste is a very unique material. So in the silver paste, so many silver filler inside, and by the contact of the each filler surface, electrical path to be formed. So in order to stable electrical connection, pressure to the D axis are very important. And because we cure the silver paste beforehand, this low modulus silver paste works as a spacer. So we can control the gap between the silver paste. So even though we press the component a lot, because of that cured silver paste bump, we can control the space, and our path mounting process is very reliable. So this is the result we have. So for that testing, we are using some dummy IC chip and a chip register, which has a daisy chain structure inside to check some electrical connection for the every point, every pins. And QFN IC and SOP and the QFP and passive component. We check that together in one board. Most of the pins show that less than 1 ohm electrical resistance, and the average plus 4 sigma is 0.7 ohm for each pins. So those are the very specific and unique low temperature SMT process we established for that synergy, the AME technology. Okay, let me explain a little bit about our AME process. For our AME process, we have some joint work with a chemical supplier to develop the good UV resin ink and a good silver ink. Our resin ink has a very low CTE and high TD, and our silver ink can be sintered at 120 degrees C, a very low temperature. Okay? So our right side picture showing some comparison between our resin and the common resin, which can be used at common 3D printer. So if we print the silver trace on the common 3D printer resin, by the swelling of the resin at the high temperature condition, so many cracks happen. But our resin, which has very low temperature and high TG properties, no crack happen. So material selection and consideration for that temperature is very important. Okay. So our circuit formation process is capable for two form, 140 200 micrometer and space without any particle splitting with low variation. So that trace width, the trace electrical conductivity. And one of the uniqueness is that roughness. So for that traditional PCB, most of the people are using the roughened copper foil or roughening chemical etching process. For that, to have the adhesion to the resin, copper surface have to be roughened. By that process, RA and RQ, the more than 1 micrometer. But in case AME, printed circuit is a very smooth surface profile, and RA and RQ both less than 0.3 micrometer. So this may mean the low loss for the high frequency target because of this smooth surface profile can minimize the skin effect. So we are expecting the application of that high frequency transfer field. The one more uniqueness of that printed circuit is the relationship in the trace width and the resistance of the trace. So common PCB circuit manufacturing process is plating and etching. The plating process has a variation within panels. And Shina copper area have a over etching as a subtract process. By them, resistance of the trace has a direct relationship to the trace width. Therefore, variation of the trace resistance is a very high in case common PCB manufacturing process, maybe plus minus 30 or 40%, I think. However, AME is a direct deposition. So critical factor for the variation is not trace width. Critical factor is a printed drop volume and the uniformity of the sintering process. Just it. Therefore, our printer variation of that resistance trace within panel is less than 10%, very uniform. Okay. The next one, the application. So our machine has AME and SMT function. Therefore, that can create the build-up circuit structure with a mounted component. And one of the direction is the value of the time. So it can be very effective for that rapid prototyping and rapid POC very fast. Another direction is that value of the design. So designing capability for that 2D and 3D. So we can make some unique structure device for that easy assembling or very lightweight module. Or if we control the thickness, bendable substrate, we can make like as a rigid flex type substrate and 3D device. And now we are trying to form the parts on the part structure. So here's just an example. So for that rapid POC and the prototyping purpose, this is one of the demonstration of that rapid POC of the IoT device. For the designing process, we designed 4 kinds of the module, which has sensor or Bluetooth or battery regulator. So it took 8 to 20 hours for each for the designing process. And after the import the data to the FM Trinity, our machine can manufacture every board within 42 hours, in case around the machine. And our latest machine target is 60, so just 1 day. And after that, assembling that every substrate and testing and check the connection to the Apple iOS. So those head-to-tail validation for designing, manufacturing, and data writing and functional validation. In this demonstration, 4 days, just 4 days we took, very fast. The 3D device is one of the target. This is an example to make the heartbeat illuminator, which has a spherical structure. And in this structure, we made some multiple boards and connected those boards via spring pin probe. And this pin is embedded in the interposer. It's also made by our printer. So by designing the 3D CAD and divide it to that multiple board, it is very effective approach for that AME and our machine to make some unique 3D device. And actually, this device is ordered by the student startup CEO, and she wanted to make this device, and she wanted to proceed the testing and the POC as fast as possible. But her concern was how to make this kind of a very complicated structure with a small volume. So that was a very good matching for our machine. So then I realized this machine can be used to that not only the B2B business model, but also B2C. This machine can provide business chance. And since our machine has both AME and the parts mounting function, sequential process, the substrate, the parts mounting, and substrate, we can try. So this is one of the demonstration. So after the parts mounting process, we print the resin again to embed the component. And since our machine has a flattening process of the resin, so resin surface is very flat. Therefore, as a right side picture, we can mount the component on it to make some structure of the component on component with an electrical connection. So, although this is a still a feasibility study level, but we are going to proceed this kind of the evaluation continuously. Okay, here's a summary. So one machine can offer us the 5-1 to the customer. So all-in-one machine with AME and SMT, and just one stop. And manufacturing is can be completed within 1 day. And since we don't require any glass mask tool and the metal mask tool initial force initial real time, from one piece we can make. And this machine behaves as a personal own factory. So this is the current project phase. So from the R&D phase we started, and we already started the sample manufacturing service in Japan, and we already built the prototype machine. And we are going to start the beta testing with a domestic EMS company soon. And after that, we are going to put this machine into the market. Okay, that's all of my presentation. Thank you for attending to today's my presentation. Thank you very much. Yeah,
Great.
that's it.
Thank you, Ryojiro, for presenting this very interesting topic to us. So I think this development, and especially the combination of two processes in one machine, is another important step in the further development of AME. Okay, we have some questions. So let's start the Q&A session, and maybe we can start a discussion about it. To participate, you can raise your hand using the reaction button, and I will activate your microphone, and then you are able to unmute yourself, or you can type your questions into the chat box. Okay, there's a first question from Frank. I will your microphone. Now you are able to unmute yourself, Frank.
Okay, can you hear me now?
Yes, we can.
Yes.
Okay, perfect. Thank you, Joyo, for this presentation. I'd like the comparison between the common PCB and the AME SMT, what you shown in the, I think at the beginning of the presentation. Can you comment on the price comparison between, or the production cost comparison between the common PCB and the AME SMT?
Okay, so it is difficult for me today to say the detail about the cost because our machines are still under development. But cost is a very important. So I think there's some sweet spot. So for the high volume production, of course, common PCB manufacturing process is a very low cost because those lines are designed for the high volume production. But in case very small volume area, we are believing we have a chance because of the consideration of the initial cost reduction. Because more tool and more tooling lead time. So and for that small volume production, not only the direct production cost, not only the tooling cost. But also lead time is important because labor cost is also the dominant. So for the small volume production, we can reduce labor cost because the very fast manufacturing, and we can reduce the tooling cost because of the direct data transfer and the direct manufacturing. Therefore, we have some area. We have advantage to the cost, and we have some area. We cannot have the advantage to the cost because I saw what I want to say is that there's some border. It can be the answer for you.
Yeah. Okay. Thank you.
Okay, great. Regarding this topic, mass production or R&D technology, we have another question from the chat from Thomas Sevchik from Tech in Czech Republic. We also have an experience with Nano Dimension from Israel regarding additive manufacturing. As you presented a slide with global forecast market size that will drastically grow in the near future. And now here comes his question. When we see current AME technology capability, do you think that technology like FPM Trinity can be used in massive production with higher volume?
Currently, no. Current our machine specification is not appropriate for the mass volume manufacturing, mass production and high volume manufacturing. It's for that small volume manufacturing process is a very fast lead time. So it's just I think that that's just a first step. So at the timing, those kind of the technology mature well, we are going to consider that next generation machine, which has more process capacity with I think the more larger build stage area or more higher number of that inkjet head or module type machine configuration or so many approach we can consider. But today's machine is not for that high volume manufacturing. But next, we can consider the technology extension to that high volume direction.
Okay, this will be then the next or the over next step then in the development of the machine then. Okay, thank you. So another question is, hello, what is the maximum protection height you are able to manufacture? So the height of the applications or products.
Maximum what?
Yeah, the maximum height of the
thickness. 4 millimeter.
4 millimeters.
4 millimeter.
Okay, thanks. Another question from Tim. Is the pick and place using tape reels or a tray for the parts?
Both we can use. So for the parts supply, we can choose both feeder or tray. So we can exchange this unit.
Okay, good. Any other questions from the audience? Okay, I see currently this is not the case. So if you have any additional questions later, please contact us. You can reach out to us from our website by using the contact me function. Also, Ryojiro is part of our community, so you can contact him directly over our platform, or you can send us directly an email. We will implement the slides and the recording for this webinar into the related event page on our platform. And let me share my screen to show where we will publish it. Hope you can see it right now. This is the event page for this webinar, and we will publish the slides and also the recording of this webinar here. If you want to go deeper into this topic, I would like to recommend to have a look on Fuji's partner webpage in our community. And here down below, above of the description of the company, you can see the latest articles from Fuji side. More will come in the future. And here you can see a lot of more detailed information about this FPM Trinity product and also the technology. So thank you for the discussion. Thank you all for the participation. Thank you, Ryojiro, for presenting this interesting topic to us. And yeah, we are appreciating your contributions. So thank you and have a nice day.
Thank you very much.